All right, before we jump into a report, I forgot, we got to do this. Where do the numbers come from? You know, where do we get our flagging protocol? How do we decide what's a yellow or a green or a red flag? How do we decide that? Well, we got over 16 million samples in our database. So if you tell us a particular make, manufacturer, model of a component, we can pull that up probably, and we're going to look at it. We're going to have a pretty good idea what the wear pattern should look like, what the trend should look like, okay? So I think that's one thing that makes us different than other labs. We don't have just a generic flagging template. It's based on the data. And each and every year, the first 2 weeks of the new year, so like January 1st through the 15th of this year, we go back and we look at all the data from 2022, and we look at our templates and we say, do we need to change any of our numbers? So we've been doing this for 22 years, so I feel like we've got a pretty good accurate set of templates set up for whatever kind of component we're going to come across out there. So another part of it is the information you provide to the lab. You know, give us good information. Good information in gives you a good report out. The OEM, you know, they'll tell us their specifications. A lot of times, though, OEMs will contact us and say, you probably have more samples on our equipment in the real world than we do. You tell us what it looks like. What should we be using for a flagging protocol? So the OEMs can have their own flagging protocol, or they may call us and say, help us with it. And we're happy to do that. Right now, we're in the process of developing a new system called Aurora. And Aurora is going to allow our data analysis team not to have to look at each and every report with a set of eyes. And what it's going to do is when we set that up, we're going to ask the customer, do you want to use Polaris's flagging protocol? Do you want to use the OEM's flagging protocol? Or do you have your own protocol? For example, we had coal mines that were contacting us and saying, hey, you're flagging this at a severity 4, and this is just the nature of the beast. You know, this is in a tough environment. You're creating noise for us. You know, this is typical. And we say, okay, what do you want to set it at? And they would tell us. And so that's their own limit. So there's going to be 3 different options now for flagging protocol, and that should be coming up hopefully in the near future. I know they're working hard on that. So the lubricant specification, tell us the brand, tell us the name. You tell us the name, that's going to tell us what the additives are in it. And then if you tell us the viscosity, that's the 3 things we need on that lubricant. You tell us that, then you tell us the OEM, the make and the model. We get those 2 sets of information. That's good data. We're going to give you a good recommendation. Okay? And then we did some statistical oil analysis, and Don Woods was our chief information officer. He passed away far too young at 59 years of age, but he did a phenomenal job of looking at the real-life, real-world data in our lab data, and he came up with the flagging protocol. So now I want to show you why it's important, if we're going to do data interpretation, why it's so important that you give us good information before we ever get started. So let's say you send in a sample and you just put on it, it's a transmission, okay? Well, we're going to go through, the system's going to go through, it's going to look at all the samples, all transmissions. And we're considering iron. We're not looking at all 24 elemental metals here for this example. So we're going to say for transmissions, it's 217 parts per million. That's a severity 1, okay? That's what we typically see in all of our transmissions. Now, you say, oh yeah, by the way, it's an automatic transmission. Now the system goes in and looks at all the automatic transmissions and says the typical iron level for a severity 1 is 149. So it went from 217 to 149. Now you say, oh yeah, it's an Allison transmission. So now we know we got an Allison automatic transmission, and it's went from 217 to 171. Now here's the kicker. Now you give us the model. Bam. Look what happened. The initial flagging point, severity 1 for iron, based on all of this information, is 68. The initial flagging point based on just transmissions, 217. If you'd have submitted that sample to us, we would have put 217 as the initial flagging point. That's probably at a severity 3, because it's 3 times this. You see the importance of the more information you give us, the better the flagging template we can pull up for you? Okay. All right. Here's just some general comments on trend analysis. We talked about it being a trend. Oil analysis works best when at least 3 samples have been taken so that trends can be identified. I will tell you it takes 75 samples for us to set up a template. based on all of our data, okay? But if we want to do a trend on your samples, we need at least 3 to start the trend. Trends over a sufficient period of time are more useful than absolute numbers when trying to determine what is occurring in a sampled machine. Yeah, the numbers are of value, and we flag the numbers. You'll see those flagged, red, yellow, green, orange, whatever color, you'll see those flagged. But it's not just that. Like if you look at the comments, one of the things I really try to stress to people, when you get a report, and let's say the overall severity in that upper corner is a severity 4, it's red. When you're looking at all the flags in the data, a lot of people don't take the time to look in the comments and look for these words: minor, moderate, significant, severe. 1, 2, 3, 4. Every time that word appears, that has an effect on the overall rating for that report. So it's not just the test numbers, but it's the times that that analyst uses a specific word. That contributes to the overall score for that report. Trending and graphing offer an easy read, instantaneous analysis of the condition of the equipment and level of contamination. I told you I've got about 30 customers where we actually take their data and we put it into scattergrams and Pareto charts and pie charts. It's just more impactful when it's visual than just looking at a number on a page. Never base a decision to tear down a machine on the results of only one oil analysis report. Anytime you get a severity 4 flag, a red flag, you will inevitably get some type of a resampling instruction. Resample at half the interval, resample a rush sample, whatever, okay? So you're going to get something like that. Again, analytical photography is the only test that we will tell somebody to shut down a piece of equipment, okay? Physical property trends help determine if the best lubricant is being used. I've got some companies out there that are doing side-by-side comparisons and saying, hey, our oil is better than the competitors, and they're using oil analysis to try to justify that. Trend analysis helps in scheduling regular maintenance, such as oil and or filter changes. You have scheduled downtime instead of unscheduled downtime. Trend analysis helps establish best practices in your maintenance procedures. Topping off will skew the data. You know, there is an opportunity when you submit a sample to put in comments to that analyst and let them know, hey, I added a quart of oil. You know, I topped off with a gallon of oil, whatever. That is beneficial for them to know. The sump or the reservoir capacity, you know, is it a 5-gallon reservoir? Is it a 100-gallon reservoir? That goes to the analysis as well, okay? And then note if multiple components are lubricated from the same sump. That's kind of a difficult thing for the analyst to have to work with. All right, okay, now we're into the data. Okay, this is where you guys get to shout back at me. And I know you can't see that, so what we've done is we've broken this down. Get this chair out of the way. So we've got a severity 4 report here. Okay? And I'm going to follow Randy's lead. Randy put these slides in and he put some highlights on it. So we see that this is what? A severity 4. 0 and 1 are considered normal, 2 and 3 are abnormal, and then 4 is critical, okay? So this is a severity 4 report. It's a diesel engine. It's a Caterpillar. Did they tell us the model? Yeah, they told us the model. They also told us the application. It's in an aggregates industry. So if I'm in an aggregates industry and I'm an analyst getting ready to look at this report, what am I going to be looking for?
Silica.
Huh?
Silica.
Yeah, alumina silica. You can be looking for dirt, absolutely. Now, one of the things you notice over here is there's a red flag. What's the reason for that red flag? When was this sampled? January the 17th. When did the lab get it? February the 15th. That's almost 30 days, okay? Our goal, when we get a sample in, our goal is to turn 85% of our samples back to the customer with a report in 24 to 48 hours. We say 85% because some tests take longer than that time period. But ultimately, we're shooting for 24 to 48 days. So if it takes almost a month to get that to us, you know, what's the value in doing analysis on that sample? One of the things that we will do is if it takes over a week to get the sample to our lab, you'll see it flagged. The date will be flagged yellow. If it's over 2 weeks, it'll be flagged red. Okay, so this was definitely over 2 weeks, and that's why it was flagged red. Okay, now we know it's a diesel engine, it's a Caterpillar, we know the model, We also know now on the lubricant, it's Shell Remula 1540. So they've given us a lot of good information. They gave us the application. So this is a good opportunity for the analyst. Now, if we take a look at this, you can see his comments. And I want you, when you read comments, be looking for those words: minor, moderate, significant, severe. They'll be in all capital letters. Remember, that's a 1, 2, 3, or 4. All right. So now we go to the middle of this report. And you guys are looking at this. Tell me what you see. We're looking at wear metals. We're looking at contaminant metals. We're looking at multi-source metals. And we're going to look at additive metals. Okay? Now, looking at all of those elemental metals, what do you guys see that's flagged red? A little louder, please. Sodium. I thought I heard somebody say it. So we got sodium at a red flag. We got potassium at an orange flag. What did we say sodium and potassium was? Coolant. So they've got a coolant leak. Is there any way to confirm that that's a coolant leak?
Copper.
Say it again?
Copper.
I didn't hear.
Copper.
No, that's, well, we're going to get there. That's good. We're going to get there. What else do we see on the report other than copper that would confirm that we have a coolant leak?
Molly.
There you go. That's the secondary. Remember those secondary inhibitors that I talked about? So when you see that moly, the molybdates, that comes in there. That's usually the first one that comes in. So now I know I'm pretty sure I got a corrosion. I've got a antifreeze leak, okay? Now, you young man, you said that what happens, the copper, okay, what's it doing?
Breaking down.
Yeah, it's attacking that. And if you think about that bearing, okay, let's say this is a bearing, a lead copper tin, what usually comes off first? The lead, okay? So the lead's already at a red level, the copper's at an orange level, getting ready to go red, and now you've got tin, you've started into that tin. So you've really, that antifreeze leak has really attacked that bearing, okay? All right, so let's see if we go through the pattern like Randy did. Sodium and potassium, molybdates are the confirming. We come over here and we see that it attacks that bearing. Very good. All right, let's look at another one. This is going to be a severity 4. And when we look at this one, we're going to see that it took over a week to get the sample. So they flagged that yellow. It's a reciprocating compressor. It's at a severity 4. What's going on here? And what we're doing here, Randy, on this particular slide, we don't give you a lot of information because this is an example of a sample that came into us and we didn't have a lot of information. So if you don't have a lot of information, if you don't know what the lubricant was, if you don't know what the OEM make and model was, that kind of stuff, that's kind of making it hard on you. So now we're going to try to figure out what's going on here. So what's the number one issue that we see here?
Silica.
Okay, we got silica, okay. And why do you say silica?
That's
What?
outside the
Okay, and what did I tell you was the limit for silica? Once it got above what, that's when we started looking for silica. 20, all right, 20 parts per million. So that is increasing. It did increase from sample 7 to sample 8. And then what happens over here to the left? The iron is going up. Okay? But before we see the iron, we also see that the aluminum, okay? So when alumina silica start going up together, that's dirt, right? And I will tell you that it's usually a 1:5 ratio, okay? Now that's not the case in this one, but oftentimes it'll be in that 1:5 range. You'll have 1 part alumina, 5 parts silica. Now having said that, I've seen it go as high as 1:13, but 1:5 is a pretty common ratio. But once that gets above 20 parts per million, let's be watching that, okay? And then we confirm it by moving over to the iron and we see the wear increase there. So that's how we confirm dirt.
Yeah, it could also depend on where that dirt is, what area or region you're in or whatever.
Yeah, yeah. And that's the type of metal that you'll see, depending on the area, absolutely. All right, let's do this one here. Okay, so that was the dirt, okay? All right, here's one where we don't have any information again. This time we don't know anything about it. We don't know the lubricant. We don't know the component type. We've got this sample here. We got to try to figure this out. What do we see going on here? We see copper, lead, and tin, okay? Look at the additive metals over here.
Wrong lubricant.
Yep. Who said that? Oh, Bill, that's good, bud. Right on top of it, yeah. It's a different additive. And look what happened from sample 3 to sample 4. You got the wrong additive package in there, and because of that, you get increased wear almost immediately. Okay? So that's how they use the additive levels. That's why it's important when you tell them this is a Shell Remula, when you give them the name of the product, that lets them know what the additives should be. Okay? So that's huge. Okay? Down here we're looking at, we got February 15th and then February the 18th. It's a year later. Okay? Wow. It's a long time. Did they change the filter? We don't know. Okay? I tell people about that area right there. When you get down here and it talks about how long the oil was in there, did they change the oil out, did they change the filter, that's the one area of the information that I never trust. Because a lot of times they'll say, you know, hey, I changed this at 250 hours, and maybe they didn't change it. You know, I just don't trust that area. And our analysts, I'll tell you, our analysts are so smart that they can tell, did you change that oil out or did you not change that oil out? Did you change that filter? Did you not change that filter? Okay, so that's the one area when I'm getting information, I always question that area. All right, let's look at a hydraulic gear pump here. We're at a severity 4. And I'm going to go back here. All right, so you can see all the information. They did a good job getting the sample to us. We did a good job getting it back to them. We know the type of pump it is. We know the model. We know what type of lubricant's in it. We know all this information. But just looking at the upper half of the report, it's a severity 4. There's nothing in the elemental metals to indicate why this should be a severity 4. Okay? Now this is a hydraulic system, and what did I say that you should run on a hydraulic system? What's one of the additional tests? Particle count. Okay? We want to run particle count on hydraulic systems, and here's the reason why. There's nothing showing up in the elemental metals, but when we go down to the lower portion here, we can see what's going on. Whoop, I went the wrong way, sorry. When we go down to here, look at that. We're starting to see the ISO cleanliness code start to increase. And it's getting larger and larger. Okay? The numbers are increasing, so it's getting dirtier and dirtier. Now why, if we're seeing these contaminants down here, why did they not show up in these elemental metals? Anybody got any thoughts, comments on that?
Too big.
Too big? Yep, bigger than the 10 microns, that's all ICP can see. That's a great answer. What else?
It's getting cut.
Getting what?
Getting cut out instead of wearing.
Okay. Again, if it got cut out, it'd probably be too large to see. What oftentimes happens is it's material that doesn't fall into those elemental metals. So let's say sometimes you got a filter and you get a fiber that comes loose out of that filter. That's going to show up in the iso particle count, but it's not going to show up as any one of the elemental metals. Okay? Sometimes with synthetics, they have some ester additives that would show up in a particle count, okay? But they wouldn't show up in the elemental metals, okay? So when the first time I saw this, I thought, wow, how can that be a severity 4? Well, that's why I say if you're running a hydraulic oil and you don't run a particle count, you don't see this, you don't know why it's a severity 4, okay? And this would be a situation where you'd immediately want to go in, hook up a filter cart, and start filtering this to try to clean it up, okay? All right, let's look at a piston pump. We don't know the manufacturer or the model. It is at severity 4. It's in a plant industrial application. We do know the sump capacity. And what do we see when we look at the middle of the report? What's their number one issue? Water, okay? Now that is 13% water. So that sample that they sent us had 13% water in it. If I asked you to convert that to parts per million, how much would that be?
13,000?
How much?
13,000?
30,000.
You got to move it 4 places. I thought somebody said it.
Oh, yeah, 130.
130,000. You know, 130,000 parts per million water. And how did they know that? Because they measured it with KF, the Carl Fisher. That told them absolutely how much water was in there. And they got so much water in there they couldn't even get a good reading on the viscosity. Okay? What did it do to the additive metals? Yeah, it diluted them. Now Randy likes to say that sometimes that much water can wash out the additives, but I'm of the mindset that, like you said, you've just diluted them. You've got so much water in that sample, it actually looks like they're at those levels. They're probably, in all reality, they're probably like samples 7, 8, 9, and 10, but they've just been diluted because there's so much water there. Okay, and then look what happens to the particle count down there at the bottom. It's got so much water in it that we can't even read it. Okay, and when we do particle count, this is an old report. If this was a newer report, we would have readings down here, because in the newer technology that we're using, we use a solvent to take out the soft particles. Water would be considered a soft particle, so that you no longer count that. In the old ISO particle counter, what would happen is it would count everything. It would count a drop of water. It would count an additive from an oil. It was counting all the soft stuff. So there was a competitor lab that came up with a new technology that they shared with all of us, and basically they take a solvent in and it removes all of these soft particles. So all that's left in that oil sample is the hard particles, which is what we're interested in. And then you would actually get a number down here. But in the old particle counter, there was so much water we couldn't count the water. All right, this is a natural gas engine. I know this doesn't apply to you, but we've looked at dirt, we've looked at coolant, we've looked at water, we've looked at those different contaminants. I wanted to show you one that's a different reason for a severity 4. This is a natural gas engine, severity 4. We know the brand, we don't know the application, but we know the OEM, the manufacturer, the model. We know all of that. It was a couple weeks late on the sample, but we can still do the analysis. We know that it's a Chevron HDX 5200 low ash gas engine oil, and it's an SAE 40. So in terms of the information about the component and the information about the lubricant, they did a really good job here. So we've got good information. We take a look at this, what do we see? Now, one thing I want to point out here is, as we're looking at this data, you see that light blue row at the very top of these samples, and it says NL. That stands for new lube, okay? That's one of those where I tell you, send in a new lube reference, and then every time you get a report, it will always show what that new lube reference looked like. So now you can look at your numbers and look back and say, you know, how much have they changed? How drastic is it? And it's a reference point for you. So I encourage you to do that at least once a year with each one of your lubricants.
What do you attribute molybdenum, the difference between the new lube and everything below it?
Remember, moly can be a corrosion inhibitor. It can be an antioxidant. It can be a multi-source metal. So maybe it's something like that.
But it's so different from everything else below it. So does that mean a formula change, maybe?
That is a significant change, Bill. You're exactly right. It's at 327. Not sure. Thinking why that would be that. Because each and every sample, they really didn't have it.
Do they cancel it out, so then it's just a reading based off of that?
Well, here's the other thing. If you move down the line, and I've never looked at this that way, Bill, thank you. When you move it down the line, look at the calcium. It's 200 points different.
What if you're running a better filter than what you're supposed to be?
Say again?
What if you're running a better filter compared to what was run at the just the normal lube level?
Yeah, I'm kind of the mindset that it's needs to be updated. You know, based on the fact that each one of those samples after that, 1, 2, 3, and 4, why would they? I mean, that's a huge difference there.
And formulas do change.
Oh yeah, yeah, and that's why, you know, I tell people to do it once a year. I'm a big fan of doing it twice a year, and I will tell you that We have a lot of these on file with the OEMs, but a lot of the OEMs, you know, they're bad about not letting us know when they make a formulation change. But that's a significant difference there. I hadn't noticed that. I want to ask Randy about that. Randy pulled this report. I'll ask him and see if I can figure out what's going on there. It just doesn't seem like it relates to the new lube reference. It's like something has changed in between. Okay. All right. What do we got going on with this? We've got copper, lead, they're elevated. What else we got? We got iron that's elevated. What's causing that? Why are those being elevated? We don't have silicon, so we don't have dirt. We don't have sodium, so we don't have potassium. Why are those being elevated? Okay, go down here and look at the bottom section of the report. What do we see? We see the viscosity has increased substantially with samples 3 and 4. We see the oxidation has increased substantially. What did we say causes oxidation? What's that? Oxidation is associated with heat. Let's go over here and look to the left. How much time is on that lubricant? 3,841 on 2, 5,707 on 3, 6,380 on 4. Did they change that oil out? No. So what's happened is the oil's been in there too long. It's been overextended. And because it's been overextended, what happened to the viscosity? What happened to the oxidation? They increased. Okay? So this is a heat situation that was brought on by the fact that they didn't change out the lubricant when they should have.